Hey, good afternoon, everyone. Welcome to the ASA SLDS webinar. Our speaker today is Professor Jiwei Zhao. Jiwei is currently an associate professor at the University of Wisconsin-Madison, affiliated with Department of Statistics and of Biostatistics and Medical Informatics. His research interests include semi-parametric statistics, the trade-off between efficiency and robustness, on domain adaptation and transfer learning, missing data analysis, and causal inference. His work has been published in top-tier statistical journal as well as in leading ML conferences. His research has been consistently supported by the NSF and NIH. Jiwei is also actively and passionately making contribution to the community. He served as associate editor for leading journals and conferences in statistics and machine learning, including the Annals of Applied Statistics (JRSSA), Scandinavia Journal of Statistics, Transaction on Machine Learning Research, AI Stats, and ICML. Here at ASA section of Statistical Learning and Data Science, Jiwei has been serving as an officer for 3 years. He was treasurer for 2 years and fixed some long-standing issues in the pipeline to make things more efficient. Now he is the program chair-elect and will be the program chair in 2026. As his colleague here in SLDS, I would say that it's really a great pleasure working with him. So without further ado, let's welcome Jiwei.
Thank you. Thank you, Zhihua. It's a very nice introduction. And good afternoon, everybody. It's my great pleasure to be here. So today I will mainly go over some of my recent research on how to do estimation and inference problem in unsupervised domain adaptation, UDA. So I will try to explain what are the settings in this type of topic and what are the main focuses of my research. So this whole background is on a terminology or topic called unsupervised domain adaptation. Across different disciplines such as in statistics, machine learning, or AI, in a more broadly defined sense, people use similar terminologies to define the very similar scenarios or settings. And UDA falls into such a type of situation. So you think about in statistics, when people talk about training data versus testing data, whenever we run a estimation procedure or do a prediction model, we always encounter such a problem that we will have a testing data that is different from training data, and sometimes we will have this so-called validation data. And also, more generally, people can say we will have source data and the target data, or like source population and target population. When people trying to emphasize these two types of data, they may follow different distributions or may just represent different cities, locations, or different situations. So that's called domain adaptation when people think if we have such type of two different data sources and how we can apply some type of technique to extract the information from one and apply to the other. So that's called the domain adaptation, or people call this is a transfer learning technique used in machine learning literature. And what does it mean by unsupervised? Unsupervised simply means in the target population, we do not observe the outcome Y yet. So you can imagine people also define supervised domain adaptation, semi-supervised domain adaptation, and also of course here the unsupervised domain adaptation. While in practice this is more practical or feasible because the target population, it might be something that you are planning to do, such as in clinical trials, or something that maybe it's very hard or expensive to collect the outcome Y data. And before you want to do the data collection, you want to first study and try to understand whether you should do that. And in that type of scenario, it's very possible that we do have the covariates X or features X, but then we do not have the label Y yet or the outcome Y yet. So far, I find there are a lot of papers, especially review papers, survey papers, and also textbooks trying to trying to talk about all the nuances or the developments under this whole umbrella of domain adaptation, especially unsupervised domain adaptation. And here I just want to particularly point out one reference that was published in 4 years ago at IEEE PAMI. It's called Review of Domain Adaptation Without Target Labels. From the title, you can clearly see this is exactly unsupervised domain adaptation. And if you search the literature, this UDA is also similarly used as the transductive, the transductive transfer learning in a transfer learning language. Okay, so this is the background. And then you can see the key question here is, what is the relation between the source population and target population, right? So if they are different versus if they follow the same distribution, and maybe the corresponding methodology in the series will be quite different. So today's talk, I will touch like 3 different scenarios. The first one is it's called the semi-supervised learning or semi-supervised inference. When people use this terminology, people trying to emphasize the we have the source data and the target data, and they will follow the same distribution. And then I will extend it to the scenarios with distribution shifts. It includes both the covariate shift and also label shift setting. So semi-supervised learning. In semi-supervised learning setting, people prefer to use slightly different terminologies. But the whole idea or whole setting is quite similar to the previous UDA that I talked about. In SSL, people will define labeled data and unlabeled data. You can see we can just regard this labeled data as the source population, where we have both X and Y. And unlabeled data U is the targeted data, where we do not have the Y. What does it mean by they follow the same distribution? So you can first think about in the unlabeled data, we do have Y, but we just didn't observe it. And then the XY joint distribution from label and the corresponding XY joint distribution from unlabeled, they just follow exactly the same distribution. So the Y given X, marginal of X, everything, they will follow the same distribution. Okay. And in such a setting, the parameter of interest usually can be defined through a theta star, that is a minimizer over a corresponding of a particular loss function, where I use L theta to denote. So this L theta, it could be like a squared error loss. It could be some other loss or very complex loss in deep learning that if you want to define. So I will more focus talking about the very standard like convex loss, where we can write this theta star as a solution of a estimating equation where we have this S function. So in statistics, we know this S function is just the derivative or gradient of this loss function with respect to the theta. And the goal is to estimate the theta using both labeled and unlabeled data. While the starting point or a very naive estimator for estimating this theta is I define as a naive estimator, which is simply use the labeled data only, just the first n samples, and you can do whatever you want. It doesn't matter what this theta is. It could be the outcome mean, it could be a least square estimator, it could be some parameter in the logistic regression, it could be anything. But basically, this is a so-called naive estimator. And the naive estimator, it doesn't use any information from the unlabeled data. Well, this is not very ideal because particularly in SSL, we may have a lot of unlabeled data compared to the labeled data size, in the sense that this capital N here is much bigger than the small n. So then you can see, or you can imagine, the whole rationale of this SSL is trying to understand how we can use the unlabeled data for estimating the same parameter of interest theta. Okay, so I will start off exploring of how to use this unlabeled data for estimating this parameter theta from the next slide. And before that, I will define function fx as the true conditional mean of this y given x. Okay. So for illustration purpose, I was just talking about how to estimate the mean, which is the expectation of y, and the whole rationale can be similarly applied to any other estimate. So the first equation I wrote on this slide, I call that is a semi-parametrically efficient estimator. Well, we need to talk about two things. The first one is, there's a f hat. I will try to avoid talking about how to get the estimator of this f hat. So you can imagine, we have all different types of tools or algorithm methods to estimate this f hat. Basically, this f hat is very well estimated. That when we derive the theory, it has all the necessary requirements or property that we would like to. So basically, f hat is just the estimate of this conditional mean function. The other more important component is I highlighted in this red box. You can see that is a ratio of the unlabeled sample size divided by the total sample size. That's a capital N divided by the summation of the two n's. Well, so there are a few things that we need to understand from this formula. The first one is, within this brackets. So this fx, no matter it is, very well estimated or it's like arbitrarily estimated, this whole brackets is a unbiased estimator for zero. Because this fx, this f hat, and also this x, they follow the same distribution across label and unlabeled. Okay, so then the point is, actually the number here, I call this red box number. It really doesn't matter of which number we want to use. It could be any value, essentially, right? Right, because the first component is just the unbiased estimator for theta. And as I explained, this whole bracket is a unbiased estimator for zero. So you can just use whatever weights that you want to create a new estimator for estimating the outcome mean. Well, then the question becomes to what type of value we can choose. Well, for the efficient estimator, the value here is capital N divided by the two n's. And also the efficient estimator needs this f to be like well estimated. But you can imagine we can replace this red box value to zero, and then it corresponds to the naive estimator that we previously talked about. And the other choice is how about we replace this red box value to 1. And then it actually becomes to a so-called PPI estimator. I will explain more in the next slide. But basically, it just means the idea of this PPI estimator is trying to understand the same estimator with a red box value as 1 using different arrangements of all the three terms. So they will put this second term here in front and then take the difference of the other two terms, the first and third terms. And the rationale is, if they are going to use the first term here is mainly the estimator for theta. And then the difference in this brackets is a so-called rectifier. And the f hat also, it could be very accurate, where then this difference will be very small. And then it also indicates this one will be unbiased. And then if this difference is large, somehow this f hat is not very accurate. And then that difference will be used to calibrate the first term estimator. So essentially, the interpretations could be different, but the whole idea is just, we combine the three terms in this way, and we can get a good estimator for this theta hat. And to elaborate a little bit more about this is a prediction-powered inference. So, in the past 2 or 3 years, there's a big group of researchers from different aspects trying to understand how this could work and how this could work better. But the original idea of PPI itself is just what I explained in the previous slide. So the delta is just the difference in the brackets. So it is used to rectify whether this naive estimator is good or bad, or how it can be, or how it can become unbiased. Okay, so let me come back to the previous slide and trying to touch base of what we are trying to do here. So this f hat, as I explained, you can use all different tools to have a good estimator. But in general, we cannot guarantee we will always have a very good estimator for this f hat. So then the question becomes to what type of red box value I need to choose so that the corresponding estimator will be at least as good as the naive estimator, which corresponds to the value here equals to 0. Okay, so here, if my explanation was not clear enough, the key point becomes to, in general, we are going to consider a arbitrary f hat. The f hat here, it does not have to be perfect or accurate. It could be very like black box predictions from AI models, AI algorithms. And then how we can guarantee the corresponding estimator will be at least as good as the naive estimator. That is basically the first equation I wrote on this slide. So I call this is a family of unbiased estimators. So I can replace the red box value as any arbitrary value omega. And then if I choose a different omega, I will have a different estimator theta hat omega. But different from the previous slide, I changed the f hat to a y hat here. The purpose is I'm trying to emphasize this y hat, we don't have a guarantee on this quality. The quality, it could be good or it could be very bad. And then the question of interest is whether we can find a good choice of this omega so that the performance of this theta hat is going to be at least as good as the first term estimator, corresponds to omega equals to 0. Okay. So you can imagine this omega, it will have a so-called optimal solution. And by calculating the variance, it's very simple algebra. By calculating the variance of this theta hat, we can get the optimal choice of omega is in such a form. Well, you can compare with the previous slide. The difference here is the previous slide, it lacks the ratio here. This ratio is a covariance between the y hat and the y versus the variance of y hat. Well, if this y hat is very accurate in the sense that it is the conditional mean function or it is y itself, this ratio will become 1, and then the whole thing will become to the previous formula. But in general, the novel development here is we are trying to say this y hat here, it could be very arbitrary, and in the sense that we don't have a guarantee of its performance or quality, and how we can still guarantee there's a better performance than the estimator which does not use the unlabeled data only. We call this is a type of phenomenon called efficiency dominance. This new theta hat, it will always have a better efficiency performance than the naive estimator here. Okay, so this is a key idea of a currently a working paper that is produced from my group. And in the SADA work, you can find this archive version. We're trying to generalize this idea to the situation that we have multiple black box predictions. You can think about the application domain could be, I have this unlabeled data and the labeled data. I can use different AI algorithms or even large language models to create some prediction y hat. Using different black box models or large language models, we may have different predictions of y hat. And then the question on top of this efficiency dominance, right? The question becomes to how we can safely and adaptively aggregate all of these multiple black box predictions. And I will skip all of those details for anyone who has interest. You feel free to go to the archive version of this paper. And actually, we are going to have a new version to be released soon. In terms of application, here's a graph that is in our SADA paper. We're trying to compare the performance of the proposed SADA estimator with PPI and also PPI++ and also naive estimator in different scenarios. You can see we use different chatbot such as GPT, Llama, and also DeepSeek. I will just use one to illustrate. So the naive is corresponds to the black curve corresponds to a naive estimator, which does not use the unlabeled data. While the PPI is a green one, the light green one, you can see in many scenarios, it actually will have a worse performance than naive. So the PPI itself doesn't have the efficiency dominance property. And then the red one and the blue one are the two different startup versions that we propose. You can see they always have a lot better performance than PPI. It will also have the guaranteed better performance than the naive, the black curve. And once we have a reasonably large sample size, small n, this blue one, it will match with the so-called oracle quite well. Okay. So this is one of the first project I try to talk about in today's presentation. And next thing I want to talk about is still under this semi-supervised setting. What other type of scenarios might emerge if we move on to the high-dimensional data setting? So I will try to talk about another paper. It's published about 2 years ago. This is a theoretical analysis with the high-dimensional data. I'm trying to explain what we are trying to do here. So we still have this, the high-dimensional model y equals fx plus epsilon. This fx is a conditional mean function. In general, it is unknown. But once we have the high-dimensional data, we usually will model a misspecified working model, such as the linear regression. So the parameter of interest, the theta star, is going to be the coefficient theta in this misspecified linear working model. And then if this is a low-dimensional problem, how to estimate this theta will just fall into the previous setting I just talked about. But if this is a high-dimensional setting, for example, if we impose some sparsity assumption on this theta, and we are very curious of what are some other theoretical properties about a better estimator for theta star using the unlabeled data, such as the convergence rate. Okay, so this whole paper is trying to understand the theory of whether we can get a better, faster convergence rate for estimating this high-dimensional sparse parameter theta star by incorporating the unlabeled data. Well, I will explain this in a little bit faster, maybe. So we started with a supervised estimator. The supervised estimator is basically the naive estimator. In high-dimensional setting, people can use this Danziger selector, theta d hat, to estimate this theta. So this red box here is the upper bound for this theta d hat. Well, it has this ratio. It has this S multiplies the phi plus sigma square root of log p divided by n. N is the sample size of the labeled data, and P is the dimensionality, S is the sparsity level. And this sigma here, it is the random error induced in this true model, y equals to fx plus epsilon, and the variance of epsilon equals to sigma squared. So because this is the random error in the so-called true model, it's reasonable to assume that sigma squared is just a big O1 term. And the other one is this big phi term. The big phi, you can see, it is a bound of the true conditional mean and also the linear working model. So if the true conditional mean function is quite close to this linear combination x transpose theta, and this phi could be very small. But otherwise, in general, we are going to allow this phi can go to infinity in some order. So in some sense that we are going to allow this phi square divided by this sigma square will go to infinity. Okay, so this red box, the value here is just the upper bound if we only use the labeled data. This is the result corresponds to the performance of the naive estimator. And then what we can do if we incorporate the unlabeled data? So this theorem can tell us the minimax lower bound, how we are going to estimate this data in a so-called optimal way, such that we can get the best upper bound for this type of estimator theta hat. Well, so you can see in this bound, it's complicated. There are two terms, but they are just due to different uncertainties. You can see the second term here, there's a sigma. So this is just due to we have the random error sigma in our model. And this term actually is irreducible because even if the linear model is correctly specified, we will always have this term. It appeared in this high-dimensional literature. But the first term is very interesting because the first term, it has this big phi term. It basically depends on how the linear model is misspecified. And then the red box value here is the ratio. And we are trying to understand what is the role of this capital N here can play. You can imagine if we have this capital N is getting bigger and bigger, maybe this whole red box value can goes to some value such like a constant C or big O1 term, right? In that sense, this term will be the same order as the second term. And then the summation of these two orders, it can becomes to something smaller. Well, that is what I'm trying to illustrate in this plot. This value here is just the convergence rate of the naive estimator. And the x-axis here is the ratio of this capital N plus n divided by small n. So you can see if this ratio, it starts with 1, as capital N getting bigger, gets up to the value of this ratio, phi squared divided by sigma squared. And then this naive order will shrink to the second order in the previous slide. And then because this one is irreducible, and then it basically means this order here might be the optimal order that we can achieve by incorporating this unlabeled data. Okay, so here is the whole idea. The higher order here is the convergence rate by using labeled data only, and then this lower order here is the order that we show that it is the best possible rate that we can achieve by incorporating this unlabeled data. Maybe it's better I will skip some details because I have some other things to present. But this is just the whole idea. And then when we're trying to create such an estimator, we realize we only need to replace one term in this score function. You can see in the score function, there's a summation across all the small n terms. We only need to replace that into the summation of all the small n plus capital N terms. And then once that is replaced, and then all other things can be correspondingly sequentially determined. Okay, so this theorem here shows the optimality of the theta hat SD, the semi-supervised dancing selector that we mainly propose in this paper. So basically, it matches with our, the theory in the minimax lower bound. Just under some conditions, the proposed estimator can indeed achieve this best rate that in the minimax lower bound. Okay. So those are the two pieces of work that I mainly present today for this semi-supervised learning or semi-supervised inference. And then I will switch the gear to talk about the situation where we will have some distribution shifts. From this outline, you can see I will first get into the so-called covariate shift, and then I will go to the label shift. So the covariate shift, it basically means from the term you can see it means the covariate will have a distribution shift. It basically means the labeled data X and the unlabeled data X, they will have a different marginal distributions. This covariate shift assumption, it indicates the margin of Y given X distribution, it will keep the same between the label and unlabeled. Well, you can see this is a paper published earlier this year at ICML. We are trying to understand a scenario where it is actually the label, the covariate shift. And the motivation is by incorporating this so-called ACP, automated computational phenotype. This is in a EHR setting, in the electronic health records setting. People are trying to develop automated algorithm for identification of children and adolescents with diabetes. The difficulty here is in this large scale clinical data network, and we have very small portion of this labeled data. because the labeled data, we need the physicians, doctors to manually review each of the cases and then to get the ground truth of the label. So this Y here just means whether this kid has this diabetes or which type of diabetes. Well, in this study, when people trying to identify the kids to manually review their charts and to provide a ground truth label, people use a so-called a stratified random sampling technique to select all of these individuals. You can imagine if a child who has very severe situations, maybe this child has a higher probability to be chosen to just review their charts, review all of the histories of the disease, and then trying to provide a accurate ground truth label. So from the design point of view or sampling point of view, it's very possible that this type of kids, their X distribution are going to be different from the kids who are not chosen to labeled. It is indeed the case. So we show there's a very apparent covariate-shift situation. In this figure is to show one of the coverts that is of interest. This is called inpatient visit count. You can see for the labeled data, the distribution is a lot more towards to 0 and 1 compared to the So the unlabeled data, their counts more towards to 0, but the labeled data, they will have a lot more ones. Okay, so basically, this convinces us to study such a scenario. It's still under this label and the unlabeled data, but under this covariate-shift assumption. And in the context of the ACP, the question becomes to more specific as I outline in this slide. The scenario 1 data structure is the setting that we do not incorporate this ACP. If I don't explain ACP clearly, the ACP is a type of generated Y hat. This is automated generated phenotype Y hat by using some type of algorithm. So in terms of terminology, it's just the Y hat, right? But again, remember this Y hat, it could be very high quality or it's not. So then the question here is we will have a corresponding scenario 2 where we do incorporate this Y hat in both label and unlabeled data. So then the question becomes to whether this type of ACP Y hat, it will also bring us some benefits such as the efficiency gain for estimating some parameter of interest. And also we try to understand where does the efficiency gain come from. Come from this labeled data or unlabeled data. In other words, the labeled data, we do have their the true label Y, the true disease status Y. And then do we still need Y hat, a so-called predicted data Y hat for this type of group of kids? So these are the research questions that we're trying to answer in this work. And theoretically, to incorporate this ACP, we also need a little bit of assumption on this Y hat. It's basically some assumptions we'll have to make, otherwise we cannot formulate this whole problem setting. This is one of the 2 results, the efficiency gain analysis. This proposition, it has a few notations, but we only need to focus on this red term. In this red term, there are 2 functions, the M0x and M0 tilde xy hat. Well, the 0 subscript 0, it means the true function, but mx, it basically means what is the expectation of y given x. Well, this s here is, we're trying to make this proposition more general. So the s is the score function, but you can just understand this mx is expectation of y given x. It's a conditional mean function. And this m tilde is a conditional mean function of y given x and y hat. Again, y hat is some ACP or in general, some predicted data by some external algorithms. So this red term here, it corresponds to how differ between the 2 functions, m and m tilde, right? Well, so there are a few scenarios that are very interesting to investigate. For example, if I solely use x to generate this y hat, for instance, in this whole database, I only have this type of x. And when we use when we use the same x or even like part of this x to generate this y hat, right? And then this y hat is going to be a function of x or part of x or something like that, right? And in that case, given x and y hat will be same as just the given x in terms of this conditional mean. Correspondingly, this m tilde and m, they are going to be the same because one is just the given x, the other one is given x and y hat. And then this red term in this efficiency gain will equal to 0. The interpretation will be, if you just use your own data to generate this y hat, in the sense that this y hat doesn't bring us any extra information beyond the data that you have, right? And then in terms of this optimal efficiency, by incorporating this ACP y hat, it won't bring us any efficiency gain. Well, I think this is very reasonable because efficiency gain, in terms of this optimality, it has to come from some extra data, extra information. On the other extreme, say if I just very randomly generate this y hat, say just random noise in the very extreme case, say this y hat nothing to do with x, nothing to do with y, just some random error. And then this y hat is going to can be ignored from this conditional mean function because y hat is going to be all independent of this y, all independent of this x. And then this m tilde will also same as this m. So this is another situation that by incorporating this y hat, it won't generate any efficiency gain, right? So this situation is also very reasonable in the sense if your y hat here is just a white noise, of course it cannot bring us any efficiency gain. Well, so for somewhere in between, in the sense that say if I use some other information that is not contained in x, say z, right? If I use z to generate this y hat, and then this y hat, this conditional mean function is going to be conditional on both x and z, for example. And then this conditional mean just conditional on x. And then this difference is going to be positive in general. So in that sense, by incorporating this y hat, it will bring us the efficiency gain. So the takeaway by understanding this result is, this y hat, it has to be somewhat informative. It cannot be something internal of the data that you have. It cannot just be some random data, nothing to do with your observed data. It has to be something relevant to your study, but it's something not contained in your current data. So in that sense, the y hat is going to be useful. And then the second question is, in a situation that we do have this efficiency gain, where does it come from? And so I think this result is very intuitive. So we understand an intermediate scenario we call scenario 3. In the scenario 3, we only put this y hat for labeled data, but not for the unlabeled data. And theoretically, we show the optimal efficiency gain of this scenario is the same as the scenario 1, where the scenario 1 is just we don't have any y hat. So you can see the efficiency gain just come from the unlabeled data, the y hat from the unlabeled data, right? This is also very reasonable result because for the labeled data, we already have the true y. So what is the point of you incorporate this y hat, right? So in other sense, if you have this true y, incorporate the y hat, it doesn't give us any benefits for estimation purposes. Okay. Again, I think I will skip this estimation procedure. This is just the cross-fitting. This double machine learning, it fits well into this setting. And the theory, it also has the traditional double robustness and also the rate double robustness and asymptotic normality and also the semi-parametric efficiency for estimating this beta. But one thing I want to point out is about this convergence rate. This is quite interesting theoretical observation. So, this small n is the sample size of labeled data. This capital M here is the notation of the summation of the two n's, small n plus capital N. So by writing the equation in this form, it may just give us an impression this beta hat is like root M convergent, consistent, right? But actually it's not. In the sense, well, what I mean is, say, if your capital N is much bigger, and you may think about this beta hat, it will have a faster convergence rate. Actually, it's not, because we show essentially it's still a root n consistent estimator. This pi will has to be absorbed into this asymptotic variance. So it means in this type of framework, even you'll have a lot of unlabeled data, like capital N is much bigger. But for developing this asymptotic normality, it's very hard to accelerate this confidence rate from a small n to a capital N or capital M. Okay, and also I use one figure to illustrate a application, and you can see the green bars are the convergence, the confidence intervals with incorporated ACP, and the red one is without. So you can see for all of these parameters of, the covariates of interest, the variables of interest, the green ones will always have much shorter confidence intervals. So it means we will have efficiency gain, efficiency dominance. But in terms of the significance readout, I think there's only this insurance type. It's quite on the boundary, but the insurance type, it changes the significance readout from not significant to significant. Again, you can check our paper if you are interested in more details. Okay, so now I will move on to the next distribution shift. It's called label shift. Label shift just means it's a counterpart to the covariate shift. It means the marginal distribution of y, they are going to be different between the two sources of data. But at the same time, we are going to assume this x given y, they follow the same distribution. In literature, there are some scenarios that this label shift assumption is reasonable. For example, if x is the disease status if y is the disease status, then x is the disease symptoms. And then this scenario might be useful. Think about the situation. The source data is you build a model, prediction model for developing pneumonia during the flu season, and the target, say during the non-flu season. And target is you want to understand the similar model for the flu season. And the y is just the flu or not flu, and then the x is the symptoms such as fever, runny nose, etc. So this x given y just means no matter it is during the flu season or non-flu season, as long as you have this pneumonia, or as long as you do not have this disease, the symptoms, their distributions are somewhat, right, arguably to be the same. But during the flu season versus non-flu season, the proportion of the disease is going to be quite different. So this is a so-called label shift assumption. I will also introduce one piece of our work. This is a lot more complicated scenario mathematically than covariate shift. So I'm trying to emphasize the notation that we use. We use P and Q to represent this source data and target data. I have this marginal distribution, the conditional distributions, and also I have this pi, which is a proportion of the source data. This is still a unsupervised domain adaptation setting. In the target data, we don't observe the label y. So our approach is we call a likelihood approach in the sense that we can write a likelihood function for a generic observation in this type of setting, label data plus unlabeled data under this label shift assumption. And then we are trying to understand what type of estimation procedures we can propose for estimating the parameters of interest. So the equation on this slide is a so-called likelihood. You can see the R is whether it is from the source or it is from the target, right? So from the source data, we do observe both x and y. So this is the decomposition of x given y multiplies the margin of y. And then in the target, we do not observe y, so we need to take an integration to y. So this rho y here, you can see it's a density ratio. It's qy divided by py. This blue term is a shared component. It's the conditional density of x given y between the two sources of data. Okay, again, for illustration purposes, I will only talk about how to estimate the outcome mean in the targeted population. But similar as before, all the methodologies can be applied to estimating some other parameters of interest. We did a bunch of work under this scenario 2 years ago, 3 years ago. We're trying to first understand the prediction model adaptation under this label shift setting. That is 2 years ago in a ICML paper. That is quite interesting, quite cute paper, where we try to convert a prediction problem into a estimation problem of we need to estimate some type of this importance weights. And we propose a method to estimate the importance weights better, and accordingly, we will have a better prediction model. But for today's presentation, I will mainly talk about this doubly flexible estimation under the label shift. This is quite mathematically more involved framework, but it's quite interesting. And we also have another working paper that we're trying to understand whether we can achieve this efficient estimation under this label shift. You can find an archive version from the website. Okay, so the key is this slide. So basically, we regard this as a semi-parametric problem. By the way, what do I mean by semi-parametric problem is, we first spell out the likelihood. You can see in this likelihood, we just have a few non-parametric components, right? The x given y conditional distribution, and also the margin of y, and also this rho y. So we call this is a non-parametric likelihood because there's no fixed dimensional parameter involved. But at the same time, our parameter of interest, the theta, it can be written as a function of the unknown non-parametric components in the likelihood function. You can see there's a x given y, there's a rho y, there's a py here. By putting these two pieces together, as long as you have a non-parametric likelihood, and your parameter of interest can be written as a function of all of those non-parametric components, this just becomes to a semi-parametric problem, and people can derive the so-called EIF, semi-parametric influence, the efficient influence function. And particularly in this scenario, under label shift, we can derive the EIF in this way. It's quite complicated, but let me explain piece by piece. So R divided by pi, it just means this first term corresponds to the contribution from the source data. And then y minus r divided by 1 minus pi means this component is a contribution from the unlabeled data, the targeted data. So there are two functions. One is rho y, this is the density ratio, and the other one is bx. Density ratio is okay, but bx is quite complicated. But what is bx? Bx is in this form, and bx, it has a ratio and in either numerator and denominator, and we will have a rho y in it, which is okay. But more complicated scenario is we have ay in this green color. And what is ay? Ay is a function of y that has to satisfy this equation, expectation of bx, plug in bx here, conditional mean equals to y. So basically, we need to understand first if we can solve this equation, and then we can get what does this ay looks like, and then plug into this one, we get how this bx look like, and then plug in back, and we will get how this EIF looks like. Okay. Assume that we know the form of this rho y and bx, and then we can just solving this empirical version of this EIF to get the estimator for theta. Okay. But to get into that, we need to know how to estimate this rho y, how to estimate this conditional mean of y given x under this source data p. So that is the EP of something given x, right? It's used in this bx function, as well as a conditional mean function of expectation given y. So here it is the same either in p or in q, but this is just the conditional mean of whatever given y, a x function given y. Well, at first sight, this looks very complicated because when we first derived this, we were expecting whether we can get some so-called robustness, right? The double robustness means if you have a EIF, it has two components. If one is correctly specified and the other one, it doesn't have to be correctly specified. But actually, this story here is quite different. So what we identify is the following. So we can just adopt a working model of this rho y. So in the sense that the rho y, you don't have to estimate it. Just plug in any working model. Basically means that we can bypass the estimation of this rho y. By the way, rho y is very difficult to estimate because we do not have the labeled y in the target data. So this qy is literally we don't have data to estimate. And then at the same time, we can also just adopt a working model for this conditional density of y given x. This term corresponds to the conditional mean function here. So it basically means we also don't need a correct model for this y given x. And what do we need? We just need a non-parametric estimation of this expectation conditional mean given y. Because the y is just a one-dimensional, so this is very straightforward quantity that we can just use the non-parametric regression technique to estimate, such as like the one-dimensional kernel estimator. And this results into our algorithm. We call this is the doubly flexible in the sense that in the whole algorithm, we do not need a true model for rho y. Instead, we just need a working model for this rho y. We call rho star y. And for this y given x conditional density, we also do not need a true model. We just need a star model. And the key is we need to solve a integral equation. That integral equation just corresponds to this conditional mean function. Conditional mean of bx given y equals to y. In the sense that we will need a kernel estimation for this conditional mean. So this is the key. So basically it means as long as we can solve this integral equation in a good way, and then we don't need any estimators for rho y, any estimators for conditional density of y given x. The name doubly flexible is we realize this is a setting that we have three nuisance components. And we can let both of them to be incorrectly specified, or in other words, we don't need their true model or correctly specified estimates of the true models. So to distinguish from doubly robustness, we call this is the doubly flexible estimation procedure. So both stars are the working models. I skipped the details of how to solve this integral equation. So essentially, this is the first type Fredholm integral equation. So mathematically, this is a difficult problem because this is an E-opposed problem. There are already a bunch of well-established procedure that people can use to solve this type of equation. So we didn't do any novel development along the line of solving this equation. We just apply the currently existing methods to solve the equation in our work. Large sample properties, you can imagine we will have this zeta hat. Zeta hat I didn't explain. It is basically the parameter in the conditional model, a conditional mean model, conditional density model of y given x. So, we only need this to be a root n1 consistent. So any estimator, MLE, moment estimator can serve this goal. And then we can get this theta hat is root n1 consistent. Well, this echoes a similar phenomenon as in the covariate-shift setting. Towards the end, the estimator just root n1 consistent. Though I use different notations here. N1 is just the previous small n. And then we derive this asymptotic variance for this estimator. The corollary is if fortunately both models are the true models. Well, this is just for theoretical investigation, right? And then we can get a corresponding estimator will achieve the semi-parametric efficiency. So it basically means it becomes the efficient estimator in the sense that no one can beat. For the comments, I've already talked about some of them. So there's no price associated with estimating this zeta. Zeta is also a nuisance parameter in this estimation procedure. Usually, if we need to estimate some extra nuisance component, it will bring us some uncertainty, right? In the asymptotic variance, we will have extra term. But for this zeta, there's no central term, so there's no price associated with estimating this such a parameter. And also the other thing is I want to emphasize the root is root n1, not root n, regardless of this pi goes to 0 or not. When I show the numerical results, I will also point out that we observe this is true in practice. Well, there's an alternative that people can also develop. We call that is a singularly flexible estimator, because as you might already observe, the y given x model in the source data, we have both y and x data. So of course, you can just build a model by fitting, say, deep learning, machine learning models or non-parametric models for this y given x, right? This model, in this singularly flexible framework, we need to perform a non-parametric machine learning algorithm for estimate. And then the singular flexible just means this rho y, it can still be a arbitrarily wrong model. A application, I only show you the results. So this is results on mean. We compare a few estimators. The shift dependent is estimator. It relies on a correctly specified rho. But in general, in practice, we do not know how to estimate the rho well. So we just plug in a arbitrary wrong model rho star. And then we have this green one is the doubly flexible and the blue one is the singularly flexible. Oracle is this is an application that we do have the labeled data. So we can just take the sample average from the, we do have the y in the unlabeled data, sorry. So the oracle is just, we take the average of all the outcome y from this so-called unlabeled data, target data. So this estimator is a root n0 consistent estimator. We call that is the oracle. So you can see the two proposed estimators, they will be unbiased compared to this shift-dependent estimator. So basically means for estimating mean, we can correct the bias by adopting a wrong model for this shift-dependent estimator. Well, we can also apply the methodologies to quantiles. Again, as I explained, it can be applied to estimating any parameter of interest. So in this one, you can see for some quantiles, the shift-dependent is going to be unbiased. But the two proposed methods will always be unbiased. But more interestingly is, for this oracle estimator, I emphasize some of the values here. So you can see in some of the scenarios, the two proposed estimators are even more efficient than this oracle estimator. Well, this is not surprising because this is a scenario that we have a lot more labeled data compared to the unlabeled data. So the oracle estimator is root n0 consistent, but these two proposed estimators are root n1 consistent. I didn't show you the details. In this application, n1, I think is 3 times or 2.5 times as n0. So numerically, by applying this technique and by, extracting the knowledge information from a lot more labeled source data, we can get a more efficient estimator than the so-called oracle estimator. So this also, again, echoes our previous theoretical investigation. The proposed estimator is root n1 consistent, but oracle is root n0 consistent. Okay, so I will wrap up. There are some take-home messages. When I talk about semi-supervised learning or semi-supervised inference, I, of course, more focus on how to do estimation and inference in this talk. And then the goal or the rationale, the motivation is just all comes from what are the benefits of using this unlabeled data and how we can use them to make sure that we'll have some type of guaranteed performance, optimal performance for estimating parameter of interest. If we have distribution shift and the main idea just comes from what is the relation between the two different distributions between source and target, right? And then whether we can transfer certain knowledge and information from source to target. I want to point out, so for all of this work that I present today, we all adopt a so-called model agnostic approach. So in the sense that we do not assume there's a true model between y and x. Sometimes we use that model, but we didn't make assumption on how that model has to look like. In the literature, there's also like a model dependent approach. See, people can make models specifically. What is a model on the source population and what is the corresponding model on target population? And then people can also study what are the differences of their corresponding models. So those are very different flavor from the work I present today. Those are model dependent approach. So to move forward, I think people might be curious of beyond the separate the covariate shift and label shift, what other type of distribution shifts people can assume, people can do, potentially a like more relaxed assumption, more general assumption. This is not very easy to do. I know a lot of people are trying to make some progress along this line, including myself. And also there are like more complex settings. Say, I didn't emphasize this, but in all of the work, especially in the under the distribution shift, we will need to assume we have the overlapped support between source and target data. So in practice, if we don't have the overlapping assumption, what we can do, or extreme case, say maybe we are lacking certain subpopulation in the source data, and then what we can do. So this is relevant to the out of distribution problem. I do have some work along this line, but it's also very difficult. It's a very difficult situation to make very meaningful progress. I will conclude my talk by acknowledging my funding agencies, including NSF, NIH, and also UW Madison Data Science Institute. And also I need to acknowledge my collaborators. All of them are wonderful collaborators, colleagues, friends for all of this work. Without them, any of this work is not going to be possible. And then I will thank you for your attendance. Thank you so much.
Thank you so much, Jiwei. Let's move to the live Q&A session.